4x4 matrix formulation. So this is a key part to the formulation of the transfer matrix method. And in fact, this is only the first part. We're looking at the field within a single layer of our transfer matrix method problem. So we have this infinite homogeneous medium, and we're looking at waves inside of that and formulating some kind of matrix wave equation that we can solve to calculate what types of field propagate in that homogeneous media. So let's get right into it. Formulation. For this formulation, we're adopting the positive sign convention. So that means a wave traveling in the positive z direction, we would write in terms of the time harmonic form as e to the positive jkz. Now we're talking about waves traveling in any direction. So waves traveling in the direction of the wave vector k, we write as e to the positive jk dot r, where r is the vector position. Well, there's a dot product here, and we can expand that, and we can write our fields this way. And that will become useful in the next few slides. So at the top, we've re-expressed our electric field in this homogeneous medium. And now we're going to consider what happens to the spatial derivatives. What happens if we take the derivative of our wave expression, and in this case, in the x direction? Well, let's go ahead and plug in our expression for the electric field. So we're interested in the partial derivative with respect to x of this expression here. Well, everything's a constant except this exponential term. So the e naught vector, e to the jkyy, and e to the jkzz, all that can come to the outside of the partial derivative. So we're just left with the partial derivative operating on e to the jkxx. And of course, the derivative is just this exponential times jkx. And so we bring the jkx to the outside. All right, now let's look at the expression left over here. This is the expression of our original electric field. So let's just write it that way. Now look at what we've done. We were taking the derivative of the electric field, and what we have seen is it's just jk sub x times the electric field. So we can go into Maxwell's equations, and anytime there's a partial derivative in the x direction, just replace it with jkx. Physically, what this means is that the only thing that's happening to our wave in the x direction is that it is accumulating phase. And the amount of phase that it accumulates is described by the x component of the wave vector. Let's do the same thing, but let's look at the partial derivative in the y direction. So again, we drop our expression down for the electric field. Now this partial derivative is only operating on e to the jkyy. Everything else inside the parentheses can come to the outside. And in the end, we just bring the jky out to the outside, and we're left with the original expression of the electric field all the way on the right. So let's just replace that with the original electric field, and we end up here. Comparing what we wrote first to what we've written last is what we can see is that a partial derivative in the y direction is just like writing jky. This tells us physically the only thing happening of interest in the y direction is that the wave is accumulating phase, and the amount of phase it accumulates is described by the y component of the wave vector. What about the z direction? Well, we could write the same thing, except we know that in the context of the transfer matrix method, our slabs are not infinite in the z direction. That means the fields will suddenly change at the interfaces. We're going to have backward and forward waves and all kinds of crazy stuff. So we cannot replace the partial derivative in the z direction with jkz. We're forced to just leave it as the partial with respect to z. So the conclusion from this slide is we simply replace the partials in the x and y directions with jkx and jky. So here's our starting point for Maxwell's equations. Notice we're normalizing the magnetic field here. So without the little tilde symbol, the little squiggly, that's our normal magnetic field. If we multiply this by positive J times the free space impedance, we get our normalized magnetic field. Remember why we're doing this. We're multiplying by the free space impedance. That makes the electric and magnetic fields the same order of magnitude. That leads to very robust numerical computation. I am also including a positive J here. This numerically does not need to be here. I do this purely for selfish reasons. And that is because now look at what happens to Maxwell's equations. Remember, one of them had a minus J, the other had a positive J, and I can never remember. Well, by putting a positive J here, not only do all the J's disappear, they both have the same sign on the right-hand side. So that's just lovely. It puts Maxwell's equations in a form that I really like. So now we're in a position to replace the x derivatives with jkx and y derivatives with jky. So over here was a partial derivative with respect to y. We've replaced it with jky. Here was a partial derivative with respect to x that we replaced with a jkx. And of course there was one here, and similar things over in this second set of three equations. So we have eliminated all of the partial derivatives except z. Now, since we've eliminated x and y, there's only one independent variable left, and that is z. That means the derivative becomes ordinary. So here's our Maxwell's equations. No more partial with respect to x, no more partial with respect to y. We have an ordinary derivative with respect to z. Let's keep normalizing things. In computation, if you think you've normalized enough, keep normalizing. It's a very, very good habit. So now, rather than have our spatial coordinates in terms of meters or kilometers or micrometers or anything like that, we really would just like to put that in terms of wavelength, which is unitless. We will do that by multiplying our spatial coordinate z by k0. Remember, this free space wave number is 2 pi divided by wavelength. So we really are normalizing our spatial coordinates by dividing by wavelength. But we've also multiplied by 2 pi. Not such a big deal. But the reason we're multiplying by k0 instead of just dividing by lambda is that it will eventually, on the next slide you'll see, it will force k0 to disappear entirely from this set of 6 equations. It hasn't done that yet. But we have put in our normalized z, but now we're carrying a k0 next to each one of those. Let's go on to the next slide. The last thing we will normalize is the wave vector, or the wave vector component. So we will take the actual wave vector components and divide them all by k0. So now in Maxwell's equations, anytime we had a wave vector component, we would multiply it by k0. That is our normalized k, and then every term in this equation would have been multiplied by k0. We divide each one by k0, and it completely disappears from Maxwell's equations. So this is a really, really nice form to perform numerical analysis on. So remember, our magnetic field has been normalized, our spatial coordinate z has been normalized, and now our wave vector component has been normalized. At this point, we have a set of 6 coupled partial differential equations. We can reduce this down to 4 by first solving the third and the sixth equation for the longitudinal components. So we're solving this first equation for h sub z and this last equation for e sub z. And here's what we get. Now let's go on to the next slide. So here's our 6 equations again, but our third and our sixth have been solved for the longitudinal components. Notice these first 2 equations have EZ in them. And we have this nice expression down here for EZ. So we're going to take this expression for EZ, plug that in up here. In our fourth and fifth equations, we have an HZ. We have this nice expression for HZ here, so we will take this expression for HZ and plug it into the fourth and fifth equations. So let's go ahead and plug in hz, and we end up with two new equations where the hz has been eliminated. We did not set hz equal to 0. We've just algebraically eliminated it. Likewise, we'll put the expression for ez into the first two equations, and we get a new set of two equations with ez algebraically eliminated. We did not set it to 0. Now we're down to 4 coupled differential equations. So here's our 4 coupled differential equations from the previous slide. All I'm going to do now is just rearrange terms. I'm going to bring all of the derivatives to the left-hand side of the equations and everything else onto the right. The other little thing I'll do is I will write this second equation first, the first equation second, and I'll also swap the order of these last two as well. And so it's really the same set of 4 equations, just with the derivative terms moved all the way over to the left. So here are our 4 equations from the previous slide. We have a set of 4 equations. What we can do now is put that into the form of a matrix equation. On the left, we have our derivative with respect to ex, ey, hx, and hy. We have our unknowns over here, ex, ey, hx, and hy. And here's all of the coefficients that came from those 4 equations, and they collect here. Notice this is a 4 by 4 matrix. Thus, we call this our 4 by 4 matrix equation. This is the equation we will solve to calculate the electromagnetic modes or the waves that exist inside of this homogeneous medium. But that is the 4 by 4 matrix equation. By the way, we're not going to get into this in this course, but here is that same 4 by 4 matrix equation for fully anisotropic media, where the permittivity and permeability are full 9-element tensors. Wish we could do more with this, but anisotropy is sort of a real pain, and we're going to move on and stick with isotropic materials. Let's look at the solution to our 4 by 4 matrix equation inside of linear homogeneous isotropic medium. We can write our 4 by 4 matrix equation a little bit more compactly this way. Remember, we had all of our unknowns, and they are a function of z. We eliminated x and y. We'll just group all these into a column vector and call that psi. Our 4 by 4 matrix, we'll call that omega. That lets us write our 4 by 4 matrix equation this way. That almost looks like a wave equation, but this is really important. That is not a wave equation because this is only a first order derivative. So this will have important consequences. That is not a wave equation, but it's still a differential equation, and we can still solve it for psi. So here's our matrix differential equation. If for a moment we sort of just forgot about this being a matrix equation and just thought of psi as an ordinary variable, what would the solution be? Well, it turns out it's an exponential. And how do we know that? Well, what function minus its derivative is 0? So what function equals its derivative? Well, that's an exponential. And so we write that as e to the omega z. And the psi sub 0, this is the state of the fields at z equals 0. So it's our boundary value, if you will, at z equals 0. This exponential term describes how those modes propagate as a function of z. So altogether, we get our fields as a function of z. But remember, this omega was a 4 by 4 matrix. How do we calculate the exponential of a matrix? It's not as easy as just going into that matrix and calculating the exponential of all the elements. That would be an array operation. This is a matrix. So we sort of have this general problem. What happens when you apply a function to a matrix A? How do we write what that is in some easy fashion? We can't just apply that function to each of the elements, so we have to do something else. The first thing we'll do is we'll take that matrix A and calculate its eigenvectors and eigenvalues. So in MATLAB, this is real easy to do. We just call eiga, and out comes a matrix with the eigenvectors and a matrix with the eigenvalues. And the meanings of these we'll get into in a little bit. But the eigenvector matrix, this is in general a full matrix, and these vertical columns represent our eigenmodes. These are pictures of our modes. We'll get more into what that means. The eigenvalue matrix, it's all zeros except numbers going down the diagonal. These are our eigenvalues. Eigenvectors and eigenvalues come in pairs. So this first eigenvector is associated with the first eigenvalue. The second eigenvector is associated with the second eigenvalue, and so on. We never want to swap those. So if we want to apply a function to some matrix A, well, this is what it equals. It equals the eigenvector matrix times that function applied to our eigenvalue matrix and then divided by the eigenvector matrix again. Now, applying this function to the eigenvalue matrix is easy because the eigenvalue matrix is a diagonal matrix. We simply just apply that function to each of the individual diagonal elements. If it was not a diagonal matrix, we could not do this. So this is a real neat way of calculating the function of a matrix, but it forces us to calculate the eigenvectors and eigenvalues of that matrix A. Let's apply what we know now about applying functions to matrices to figure out what to do with this matrix exponential. In this case, our function that we're applying to this omega matrix is an exponential function. So the first thing we'll do, once we build that omega matrix, is calculate its eigenvectors and eigenvalues by calling eig. Once we know that, our matrix exponential is simply the eigenvector matrix times that function applied to the eigenvalue matrix divided by the eigenvector matrix again. And this exponential applied to our eigenvalue matrix is easy because we just simply apply a standard ordinary exponential to all of our eigenvalues. Now our solution, which was written as this matrix exponential, we can now write as w times e to the lambda z prime divided by w times this size 0 prime. Remember, this is a column vector, which really represents our fields at z equals 0, and that's not known yet. So if this is a column vector of unknowns, here's our eigenvector matrix. We invert it, but this just gives us another square matrix again, but this will be known numbers. But if we take a square matrix of known numbers and then pre-multiply a column vector of unknown numbers, we simply just get another column vector of unknown numbers. So why keep doing this? Let's just group these together and call this a column vector of unknown numbers. And so that's exactly what we do, and it saves us some computations. Okay, so we had a matrix differential equation, and we're now writing the solution this way. The eigenvector matrix times the exponential applied to the eigenvalue matrix times a column vector of unknown coefficients. So mathematically we have that solution. Let's try to get an intuitive feel of what that solution means. So here's what I like to call the anatomy of the solution. Let's look at this one term at a time. Well, the psi term, that's the overall sum of the fields. If we can plot that as a function of z, we would see our x component of the electric field, our y component of the electric field, our x and y components of the magnetic fields. So it's the overall final solution as a function of z. W is our eigenvector matrix. This really is the picture of the modes. It doesn't really tell us the amplitude of the modes. It just tells us relatively the magnitudes of E and H with respect to each other. It's not telling us how much power or the amplitude of that mode, just the pictures of the modes. The exponential is telling us how that wave propagates. Does it oscillate? Does it decay? Does it do both? Maybe it grows if there's gain. So the exponential term is telling us what happens to that mode as it propagates. The last term, these are the mode coefficients. This is what actually tells us the amplitude of the modes, or how much power is in each of the modes. It's amplitude quantity, so think in terms of amplitude. So here's an example to get us a feel for the numbers. Let's say we have a medium that has a dielectric constant of 9, no permeability, or so just a relative permeability of 1. This means it has a refractive index of 3, right? Because the refractive index is the square root of permittivity. Let's say there's a wave at normal incidence, so that means our kx and ky components are 0. If we were to follow our recipe, this is what we would get for the omega matrix. All right, let's go ahead and calculate the eigenvectors and eigenvalues of that. Well, what does this mean? That's what we want to get into. But remember, the eigenvector matrix is pictures of the modes, and the eigenvalue matrix is telling us how these modes propagate. Let's dig into this a little bit more. So remember, the top row in the eigenvector matrix, these are our x components of the electric fields. Second row is the y component of the electric fields. Third row is the x component of the magnetic fields, of course normalized. And the last and fourth row is the y component of the normalized magnetic fields. We don't know yet what the z components are, but given the x and y components, we can go back to those original equations where we solve for the the EZ and HZ components and figure out what those are. But we don't really care about that now. So we only know EX, EY, HX, and HY. And I've written the eigenvalues right below them. So we can see, okay, this eigenvector is associated with this eigenvalue, this eigenvector is associated with this eigenvalue, and so on. Let's look at the first mode. So a mode is a combination of its eigenvector and eigenvalue. Well, it's telling us the x component of E is a minus j 0.32. So we have an x component of our electric field, and the amplitude is minus j 0.32. And we can see that here. It has no y component, so there's no blue vectors pointing in the vertical direction. There is no x component of the magnetic field. So there's no red vectors pointing this way. However, there is a y component of the magnetic field, and it has an amplitude of 0.95. And so there's our magnetic field in the y direction with a magnitude of 0.95. Now, it has an eigenvalue of j times 3.0. So that means what would describe this mode propagating is e to the j 3.0 times z. So this is a wave traveling in the forward z direction because we're using the positive sign convention. Let's move on to the second mode. This only has an x component of E and a y component of H. Looks very similar to this first mode. The only difference is the sign of the E component is different. And the sign of the eigenvalue is different. Since the sign of the eigenvalue is different, now our exponential is e to the minus j3 times z. That means we have a backward wave. And the difference between the x component of E is one has a negative sign, so our electric field is now pointing in the opposite direction. And if we think of the handedness of E and H in terms of the direction the mode is going, this makes sense that the electric field would have to be in the opposite direction. We could have put the magnetic field in the opposite direction, but that's not what the eigenvalue problem gave us. On to the third mode. This has no x component of the electric field, so we are going to expect this to point vertically now, but it does have a j times 0.32 for the y component, and that's exactly what we see. We see the electric field pointing in the vertical direction with an amplitude of j 0.32. By the way, what does that j mean? That just means it's 90 degrees out of phase with respect to the magnetic field. And of course, I had the same meaning up here, so it was 90 degrees plus another 180 degrees. Okay, so we have a y, the electric field pointing in the y direction, and the magnetic field now pointing in the x direction. And that's exactly what we see. The eigenvalue is a positive j 3.0, so our exponential is e to the j 3.0z. That's a forward wave. On to the last mode. It only has a y component of e and an x component of h. Same as that third mode, but there's a negative sign on the e. So that's exactly what we see. Now the electric field is pointing down instead of up. And for the eigenvalue, we have a minus j 3.0. So our exponential is e to the minus j 3.0z. That means backward propagation. So from this, I'll say it again, the eigenvector matrix, that's the pictures of the modes. It's just the relative amplitudes of the electric and magnetic fields with respect to each other. This is not telling us the amplitude of the mode. That's in the mode coefficients that would be multiplying this. And the eigenvalue matrix is telling us how these modes propagate. Let's dig into the meaning of the numbers in the eigenvector matrix a little bit more. What does that mean that it's 0.32, 0.95? Why can't we just choose any numbers for the electric and magnetic fields? Remember, the magnitude of E and H are related through the material impedance. Now we have a normalized magnetic field, so that equation for impedance is a little bit different in that we just have the square root of the relative permeability divided by relative permittivity. And if we run the numbers, this is 1 over 9. Square root of that, we get 1 over 3. Well, let's check the numbers. The electric field was about 0.32. I know we had minuses and j's, but it's 0.32. The h was a 0.95. If we look at that ratio, it's 1/3. So really, the numbers here between the e and the h is enforcing the impedance. It's making sure that that is balanced. So one thing we could do, and this is along the lines of trying to explain that this is just the pictures of the modes, not really explaining the amplitudes. So what if we took one of these columns and just doubled it? So 0.64, 1.9, if we looked at the ratio, it's still 1/3. In fact, this would work. It would just be, if we ran a simulation with it, the mode coefficient would be half of what it would be if we had retained the first numbers. So amplitude is really not being conveyed in that eigenvector matrix. It's only the relative amplitude between E and H that matters, because that's what's satisfying the impedance of the medium that the wave is in. Now let's think about the physical meaning of the eigenvalue numbers. Well, our waves are propagating according to e to the lambda z. Well, we also know that our waves propagate e to the j, and if there's an angle of incidence, we'll throw in cosine of the theta, angle of incidence, times z prime. So if we compare these, that tells us that our eigenvalue is j times refractive index times cosine of our angle of incidence. Well, in this case, our angle of incidence is 0, so cosine of 0 is 1, and we're just left with our eigenvalues equals j times refractive index. Well, if we calculate the refractive index of our layers, it's 3, right? 1 times 9, that's 9, and then of course the square root of that gives us 3. And that's what we see. We see 3s over here. So those eigenvalues in this context of transfer matrix method is really the effective index of the wave in the medium. And of course, if there's an angle of incidence, that would change a little bit. And there's also this j in there. But that's the physical meaning of the eigenvalue numbers. It's essentially our refractive index.
From the bottom of my heart, thank you very much for watching this video. I love hearing your stories about how these videos helped you. I also love answering your questions. So please tell me your stories and ask your questions in the comment section. I promise I will try to answer every single question that's asked. If you like this video, hit the like and subscribe button. I also recommend visiting the official course website that has links to the latest versions of the notes, the latest videos, and there's lots of other resources to help you learn, including implementations in MATLAB. I'll see you in the next video.